So I said there are three ways to move things or affect the speed of the GI tract, especially the stomach. There we go. So I said the stomach controls the stomach, and if I have a lot of volume, does the stomach move slower or faster? This is the stomach. If you put a lot of food in the stomach, it wants to move faster. It either wants to move it quickly downward or it wants to move it quickly back upwards. So if it's something that's very what? Dry or very wet, it'll move it downward faster. Very wet. The more wet it is, like if you do a Chinese buffet and you put a lot of volume in there, very wet food, it's going to push it through you a lot quicker. And then the fluidity, I give the example of going out on a Friday night. If you drink a lot of fluids and you don't eat very much food, the fluid shoots straight through you. And then that was stomach controlling stomach. What's the other thing, the second thing that was controlling the stomach? Where's the stomach pushing the food to now? The small intestine, the duodenum. So now it's the duodenum. If it's high fat, does the duodenum speed up the stomach emptying or slow down the stomach emptying? Slows it down. So the duodenum, the small intestine, has a thinner lining. It can't handle things like fat, processing fat, or acidic materials, or really thick, chunky stuff. So any of these factors will tell the stomach, whoa, slow down, you're giving me stuff that's not ready to be processed yet. Like the fat. We have to slow down and slowly process the fat to get as much as we can out of it. The acid, if you push stomach acid into the small intestine's pH is a little basic. So what's the small intestine have to do if you push a bunch of acid stuff in there? What's the N word that you hear about stopping acids from destroying things? Neutralize it. You have to neutralize it. So the more acid that the small intestine receives, the more it has to neutralize it. Does anybody remember the B word for the chemical that neutralizes acids in the GI tract? B. B is in boy, or bicarbonate. Bicarbonate. And then hypertonicity is saying that the stuff's really thick. It has a lot of solute compared to what? Hypertonicity. When did we learn about that word? When we talked about what O word? Osmosis. We were talking about water concentrations. So if it's really thick, the small intestine can't handle it. So what it's going to do is it's going to take some time, dilute that food a little bit more, and then push it along. So any of these factors are telling the stomach, you're pushing too much in, I can't process it fast enough to slow down. And then the last thing was what organ controlling the stomach speed? It's all in your head, right? Your head. Things like emotion can do that. Then we talked about vomiting not being reverse peristalsis. Peristalsis is that slow movement, squeezing down. Vomiting, everything just opens up, the stomach squeezes, diaphragm squeezes, everything squeezes and pushes the food up and outward. Okay, so secretions. There's your next section. Where the secretions come from are the lining of the stomach, and there are two primary regions, the oxyntic region and the pyloric region. The oxyntic region is the top part of the stomach, fundus at the very top, and then the body where you're storing things. So they're almost like the pre-wash area. They spray the food with this substance to try and start breaking down the food slowly. The pyloric glands, what actually does like the really strong mechanical contractions to smash the food apart. Like you said with the blender, that's where the blade would be basically. You don't have a blade in your stomach, but it does a lot of smashing down there and a lot of trying to squeeze. So oxyntic's the first two regions and pyloric's the last one, right before you go into the small intestine. Right. So again, there's the top part, the fundus in the body, or the oxyntic region, and then down here's the pyloric region. What do you call this round piece? Oh, it's labeled. Never mind. I was going to say, what do you call this round piece of muscle that prevents food from moving to the next section? Sphincter. In any part, whether you're talking about going from the pharynx into the esophagus, there's a sphincter there to prevent things from going when they're not allowed. And from the esophagus to the stomach, what's that preventing? The one between the esophagus and the stomach. Reflux. Yep. And then from the stomach to the small intestine, then we'll see the same thing from the small intestine to the large intestine, and then rectum out to the anus. Okay, so when you slice away a part of the wall of the stomach, this is what it looks like when you look really close. You can see these large pits. And these pits contain all these specialized little cells that release chemicals or secrete chemicals. And these are definitely ones you have to memorize. So I'm actually going to talk about them twice. Briefly right now, and then in better detail in just a bit. So the four types of cells you find in the walls are the mucus cells, and guess what they release? Mucus. The chief cells release something called pepsin-ogen, Anytime you ever see the word ogen or the suffix ogen, it means it's not active. When this stuff's released, it doesn't work yet. It's extremely toxic. It's a really toxic enzyme, actually, that breaks apart protein. You are made of lots and lots of protein. You don't want this just to be activated anywhere because it would actually eat you. And the parietal or actinic cells, these release, what's HCl? Hydrochloric acid, right? So it's acids. And this chemical called intrinsic factor, which is really important, and we'll talk about this in anemia, which you probably didn't even think about the stomach being able to control your ability to have anemia, or ability to, causing anemia. But we'll talk about that again. And the last one is the enterochromaffin-like cells, or the ECL cells, is the abbreviation. And they released histamine. And you probably associate histamine with allergies, but not all the time. Histamine has other purposes in your body too. We'll talk about those. So 4 major cells that you find up here in the actinic region. These are like the preparatory cells. The food drops in, the big chunk of apple pops in, and it's almost like pulling your car into the car wash, and that foam sprays across it while it's prepping it to wash the car. That's all that's happening here. You're spraying these chemicals all over your food to prep it to be digested. When you look at the glands, here you can see the surface. This is, what's the L word for the hollow part of the GI organs? The lumen. So up here's the lumen, and you see these are where all the cells are at that are going to push their chemicals out into the lumen to start digesting things. So up at the surface, these green cells, these are surface epithelial cells, but they're also mucus cells. There's a difference between these mucus cells and these down here. The ones at the surface release a thick bicarbonate mucus. Why would you want to do that? Why at the very surface of your stomach would you want to release a thick bicarbonate mucus? Neutralize the acid, right? The bicarbonate is to neutralize the acid. The thickness is to try and slow the acid's penetration so it gets a chance to neutralize. So up at the surface you have that thick, sticky mucus, but it's full of bicarbonate is kind of the key. As you get further down into the gland, it's a watery mucus, extremely liquidy. And what it's actually doing down here is it's washing out all these chemicals to the lumen. So it's like spraying some water in here to try and clear all this out and get it out into the lumen. Otherwise, those chemicals would just sit there and eat your stomach wall. So 2 types of mucus cells. The ones at the surface are thick, sticky bicarbonate. The ones deeper are very watery. And then the chief cells, what was the name of the chemical I told you they make and release? Pepsinogen, right? And then the parietal cells release 2 things. Hydrochloric acid and intrinsic factor, which you'll usually see IF, but it's capital I, capital F instead of if for intrinsic factor. And then the ECL cells down here at the bottom release histamine. So these mucus cells or mucosa cells will secrete this water. The water comes in, flushes all of this stuff up, and pushes it out into the lumen. As you get down deeper into the pyloric region, down by where you're about to go into the small intestine, you see different cells. You see G cells and D cells. And G cells release gastrin, which we'll talk about in a little bit. D cells release something called somatostatin. I wish they would just call them S cells, but they don't. But if you notice, these cells that were up in the body part are not down there because these things are releasing chemicals that eat proteins that are very acidic and very toxic. Why would you not want those right at the border or the doorway of the small intestine? What could they do? I keep telling you over and over again, the small intestine is very delicate, is gentle, and you're releasing the stuff that's very toxic. You don't want that to happen down by the doorway. So you release this in the body, and these last couple steps are right there along the pyloric gland. Okay, so the gastric pits. The mucus, by the way, where is the mucus released from? They're also released from mucus cells. So it's not a big trick. So mucus released from mucus cells. There's a little tiny bit of pepsinogen, but barely any at all. It's more like it's the closer you get to that doorway, the sphincter, the less and less pepsin you get. There's absolutely no acid released there. Why again? Because you're about to push right in the small intestine that needs a basic environment. So if you were to push acid out here, you're just going to push it straight into the small intestine. And it totally defeats the purpose of the acid. And then I already said this, but the G cells release gastrin, D cells release somatostatin. These are both hormones, I would underline them. They'll come back again and again and again. Somatostatin, in fact, I know 3 other systems we'll talk about that release the exact same chemical. So somatostatin will be back. Somato means, anybody know what somato means? Or soma? It's Latin for the body. So somato is referring to a body. Statin means to hold it static or to stop it. So guess what this hormone does? Stops everything it comes in contact with. If it comes in contact with acid-releasing cells, it stops them. If it goes up to your brain, your hippocampus, it tells it stop eating. It stops it. If it goes to your pancreas or it goes to the pancreas and affects a cell that releases insulin, what's it going to do to that cell? If you had to go with your gut, what would you think it's going to do to that cell? Stops it. It stops everything. It's a very angry hormone. So if I ask you a question like this, chief cells secrete what? What do the chief cells secrete? Well, we can make this easy. How about number 4? Chief cells secrete mucus. What secretes mucus? Mucose cells or mucosa cells. So we know that one's wrong. Here's another trick if you don't remember. Is there a cell in there that releases more than one chemical? Yes, there's a cell that releases 2 chemicals, which are what 2 chemicals? HCl and intrinsic factors. So is it possible to have number 1 and number 3 to be right in this question? No. So it has to be pepsinogen. So if you forgot, then you can narrow it down. You know, mucus cells release mucus, and then HCl and intrinsic factor from the same type of cell. So it's impossible to have 1 and 3 both be right. So it had to be number 2. What else do you know about pepsinogen? What's its secret? Well, it's pepsinogen. It's inactive. It's not active yet. All right, so let's follow the process. I love this picture. I thought it was funny. But it actually shows the secretions too. Here's a secretion, one secretion going into the mouth. What would that secretion be? Saliva. And you're chewing, you're processing, you move the food down as what's the B word for this? Bolus drops into the stomach, and there are 2 major chemicals that are secreted that digest food. One's hydrochloric acid, and the other one's going to be an inactive chemical that we're going to activate. Pepsinogen. Yep. The 2 major digestion chemicals. And then you go to what would this next pathway be after the stomach? Small intestine. Yep. In the small intestine, we're going to talk about things that break down lipids, carbs, and fats. Lipids and fats. Redundant. Lipids, carbs, and proteins. And then as the food moves through, it's all processed and gooey. Now you're going to start squeezing the nutrients out of it. You're going to push it into the large intestine. You're going to extract water, and then flush. I don't know why his pee is dripping into a coffee cup either. I just don't get that. I don't know what country that is. All right, so exocrine product details. Exocrine means you're pushing it where? Out. Does that mean out of the body or out into the GI tract? In this situation, it's out into the GI tract, into the lumen. All right, so the chemicals, we're going to go through them each individually. Hydrochloric acid doesn't technically digest. Just a technicality here. Hydrochloric acid does something called denature. I think it's on here somewhere. Right there, number 3. Denature is the key word. It doesn't digest. You have to think of protein. Protein's like a ball of yarn. You've got this nice tidy ball of yarn. What hydrochloric acid does is takes that ball of yarn and throws it. Did you actually change the structure of the yarn? No, the yarn's still exactly the same. All you did is rearrange it a little bit. It's still exactly the same. What hydrochloric acid does is stretches that protein out. It straightens it out because proteins ball up, they curl up. So it re-straightens it out into this nice, fine, string-like structure. And then what we're going to see is the next chemical, pepsinogen, will come along. It's the scissors. Clip, 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 clip. If you took a pair of scissors, let's say you took those kindergarten scissors, and you had a ball of yarn, is it easy to cut that ball of yarn in half? So what would you do to cut the yarn? You'd unroll it. That's what hydrochloric acid does. It unrolls the yarn so that pepsin can come along and clip it up. What are you cutting proteins into? So in other words, pepsin is trying to take the big protein and turn it into little tiny, starts with an A, amino acids. Okay, so number 1, It converts pepsinogen to an active form, which is called pepsin now. So these two chemicals come together. Pepsinogen is like a hand grenade. It's just waiting for the pin to be pulled. Hydrochloric acid is the pin. Number 2, aids in breakdown of connective tissue and muscle fibers. When you eat a steak is a good example to think of. You have all that connective tissue. You have all those muscle fibers, the red meat. They're all proteins. They're just different arrangements. It's like the tendon's made of protein just like the muscle is. It's just a different arrangement. Hydrochloric acid starts breaking them apart into longer strings instead of big wads. Number 3, denatures protein. And denature, again, was the key word. So in other words, it uncoils the protein. Tertiary structure is a biochemistry term, but it's in your book. Tertiary structure just means that when you take all these amino acids and you line them up, and then you start curling them, and they curl them over themselves, you have this three-dimensional structure. That's what they're referring to. So it takes it from a three-dimensional structure and flattens it out, so it's easy to process. And then number 4, along with salivary lysozyme, it kills most of the bacteria and viruses that you ingest. Are there any bacteria that your stomach acid won't kill? Yeah, you probably heard about it. Back in the 80s, everybody denied this bacteria existed, but a guy pulled samples actually he pulled some out of his own stomach, and looked at them, and there was bacteria growing. Anybody know the name of the bacteria? It's called H. pylori, Helicobacter pylori. And it's one of the primary causes of stomach ulcers. But acid doesn't kill that. It loves the acid. What it actually does is it puts on an alkaline coat. It covers itself in an alkaline material, ammonia, and then just swims around in the stomach acid. Doesn't have a problem with it. Okay, where is hydrochloric acid borrowed from? I hoped I'd pushed this hard enough. Maybe I didn't. Where's everything that's secreted borrowed from? The plasma. Yep. So here you have the plasma or the blood on this side. What happens is you'll take things like carbon dioxide, some water in here, you mix them together into this long reaction with carbonic anhydrase to turn them into carbonic acid. Then you separate the hydrogens and you push the hydrogens out into the stomach. Have you seen this equation before? Yep, it's a famous equation, right? We talked about when we talked about red blood cells and carrying bicarbonate through your system. It's the same process, but instead of doing this inside of a red blood cell, it's doing it inside of an intestinal cell or stomach cell in this situation. So it'll take that hydrochloric acid and push that out, and then it takes a chloride ion, chloride shift, remember we talked about that too? The chloride can shift into the wall of the stomach, goes all the way to the other side and kicks out. So the chloride and the hydrogen will actually stick together and form hydrochloric acid. And then it's pushed up into the lumen of the stomach to start digesting food. So it's really a complex process. And if it's borrowed, what do you know has to happen? It has to be reabsorbed. So when we get to the small intestine, we'll see that this process, this breaks down proteins inside the stomach, but when it gets to the intestines, it's neutralized with bicarbonate, and then it's reabsorbed. It just goes right back to this process. It takes the bicarbonate, the hydrogen ions, reverses it, and then pushes the CO2 in. Same process, just reversed. Next chemical is pepsinogen, which you know is inactive. But once it's activated, it starts breaking down. It actually digests. So here's digestion instead of denaturing. What activates pepsinogen? Hydrochloric acid. Yep. So hydrochloric acid will actually find the pepsinogen. So here's the cells in the oxyntic region. Here you have HCl being released from a cell. It gets pushed out and into the lumen. Over here you have pepsinogen being released from a cell. It gets pushed out to the lumen. They find each other. The hydrochloric acid cleaves or cuts that pepsinogen, and now the pepsin is active and can digest proteins. It'll go along like a pair of scissors to just clip apart the protein, one amino acid at a time. Clip, 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 clip. Here's the scary thing. Once you activate a little pepsin, it activates more pepsinogen to make more pepsin, which activates more pepsinogen to make more pepsin. That activates more pepsinogen to make more pepsin. What am I trying to point out here? What kind of loop is that? It's a positive feedback loop. Would it be possible that this could be dangerous? Yeah. If you make too much pepsin, pepsin digests proteins. What are you made out of? Proteins. Your stomach is made out of proteins. Your bones have a protein skeleton. You're protein everywhere. I was actually just listening to the Da Vinci Code book the other day. In the very beginning, the guy got shot in the stomach, and they started describing how his stomach would actually eat him from the inside out. And I thought, oh, let me explain this for you. But that's exactly what happens. If this stuff gets through the stomach wall, it'll eat everything in the abdominal cavity. It doesn't care. Pepsinogen is a dangerous chemical. So when we get to the small intestine, we need to take care of it. We have to stop it from working. Pepsinogen is an enzyme. It just speeds up reactions. Every time you see an enzyme, it's also made out of a protein. So the irony here is that hydrochloric acid will activate pepsinogen. Pepsinogen will activate more because it just it cleaves or cuts that protein in the right spot that activates it again. But eventually, pepsin can start eating more pepsin. So it's almost like a little group of cannibal enzymes inside of your stomach that will eat everything. Right. Next cells are the mucosal cells or mucus cells. And they, of course, release mucus. If it's closer to the stomach lumen, what kind of mucus do they release? Watery or thick? Thick. If it's closer to the lumen, what's that other B word that they also release a lot of? Bicarbonate. Yeah. So again, here you can see the lumen. Here you can see the mucus cells pushing out all along the surface here, this thick mucus coating, so that when hydrochloric acid hits it, it's slowed down. And then the bicarbonate will actually neutralize the hydrochloric acid. Once this hydrochloric acid is neutralized, you can actually reabsorb the hydrogens and the chlorides and the bicarbonate and everything. All right, next is intrinsic factor. And intrinsic factor, I already told you, is important in what disorder? Anemia. I thought it was on here. Maybe it's not. Oh, yeah, there it is. Right in the middle. So decreased levels will result in pernicious anemia. There are a lot of types of anemia. This is just one type. Intrinsic factor is kind of cool. Intrinsic factors, it's almost like an escort. It finds vitamin B12, it holds onto the B12, and then escorts it through the stomach and into the small intestine. Once it's in the small intestine, as long as those two chemicals are bound, B12 to intrinsic factor, it'll pull it into your blood. If you have one without the other, they can't cross. So people that get like a bypass surgery and they don't have enough intrinsic factor meeting up with their food, what might they have a problem with? Absorbing B12, what disorder could they get? Pernicious anemia. People get a lot of ulcers if they destroy the cells that release intrinsic factor. Just as we age, we release less and less intrinsic factor, which as you get older, you have a higher risk of getting pernicious anemia. So B12 is the important thing. Intrinsic factor binds to the B12, that's what the plus is for. And then when those complexes are together, when they get to the terminal part of the small intestine, is the ileum, then they get absorbed. This is almost redundant. Terminal means the end. What part of the small intestine is the ileum? It's the end, right? Duodenum, jejunum, ileum. Okay, so digestive juice regulators. We talked about regulating the speed of movement through the stomach. Now we're going to talk about how you regulate the juices. So the first one's gastrin. Where was gastrin released from? Was it the oxyntic region or was it the pyloric region? I only mentioned it once, so I don't expect you to memorize it, but it's not the oxyntic. We just covered the four types of cells in oxyntic. G cells are in the pyloric region, right next to the small intestine. And gastrin is a hormone. All right, so gastrin, what causes its release? Parasympathetic stimulation. What neurotransmitter should you automatically associate with this? 3 letters. ACH, acetylcholine. And another stimulator is the presence of protein down at the very bottom of the stomach. By the time that protein gets to the bottom of the stomach, it should be mostly processed, so you shouldn't have a lot of whole proteins down there. You can have little fragments called peptides. But they should be processed primarily up in the body. When they get down to the pyloric region, they should be mostly processed. So if you have a lot of protein down there at the bottom, you release this chemical that goes back up to the oxyntic region and says, release more hydrochloric acid and more pepsin. Why would it do that? Think about it. If gastrin is released because there's protein, and gastrin goes to release hydrochloric acid and pepsin, why did it do that? Because it wants you to break down those proteins. This is interesting. This is actually one of the first times you'll really want to pay attention to a negative feedback loop and commit it to memory. So If you have protein, high protein starts this loop. High protein down the bottom of the stomach turns on the loop. Gastrin is released, it goes up to the body, and it tells the body to release hydrochloric acid and pepsin to break down this protein. Now it's broken down the protein, what happens to these G cells? Do they turn up higher or do they turn off? They turn off. The initial stimuli was having high protein present. This chain turned on to destroy the protein, which now you have low protein, and it turns off the chain. It's a negative feedback loop. And then histamine, they're released from enterochromatin-like cells, ECL cells. These are actually in the oxyntic region. Histamine in this situation is considered a hormone. Right? So ECLs are stimulated when they're stimulated by gastrin, the chemical. So when gastrin comes up, it stimulates HCl release, pepsinogen release, and also histamine release. But histamine also increases hydrochloric acid secretion. This is tricky. Histamine we usually, and this is how I remember it, histamine we associate with what, typically? Allergens, some kind of an infective agent, whether it's pollen that's infecting you or it's a bacteria that's infecting you, something getting into you. So what could you think of that would make you think histamine is going to release hydrochloric acid? What's the hydrochloric acid going to do to this infective agent? If I took pollen and dumped acid onto it, what do you think would happen to it? It destroyed it. If I took bacteria and dumped acid onto it, what do you think would happen to it? Destroy it. Virus, same idea. Histamine is released when anything stimulates this wall that shouldn't be there. So it stimulates histamine release, which stimulates hydrochloric acid release, which kills whatever that stuff is. I almost said infective agent again, but I just gave that as a general term. It can be anything irritating the stomach lining. Somatostatin, what do you already know about this one? It likes to do what to everything else? Stops it. It's a hormone, it can travel through the body, and it stops everything it comes in contact with. Somatostatin stops growth hormone, so what could this make happen to you? Yep, it could make you have stunted growth. Yep, it could decrease your activity of like bone-making cells, muscle-making cells. It stops everything it comes in contact with. Right? The cells it comes from are called the D cells. And right now, like I said, we're going to talk about it over and over again, but right now you have to remember in the stomach it stops acid secretion. It stops it. It doesn't want acid to be released. So again with the acetylcholine, what system releases acetylcholine? Sympathetic or parasympathetic? Yep, the para. So when we're talking about those postganglionic neurons releasing acetylcholine, those are all parasympathetic. Postganglionic neurons that release norepinephrine are all sympathetic. So anytime you think of acetylcholine in your GI tract, gut instinct, what should you want to say? Does it speed it up or slow it down? Speeds it up. Acetylcholine typically speeds things up in the GI tract. So acetylcholine, gastrin, histamine, all of these speed up the release of hydrochloric acid. Bless you. Acetylcholine and gastrin speed up the release of pepsinogen. So these are the two primary focuses. Both of these things you're focusing on, hydrochloric acid and pepsinogen, what are they trying to destroy or break apart? Pepsinogen is trying to digest proteins. Hydrochloric acid is trying to what proteins? It's not digest. Denature. So if you've noticed a theme, and when I was looking through the chapter, I really noticed in the stomach there's one thing that it really focuses on breaking apart. What do you think it is? Proteins. What do we focus on in the mouth? What's the mouth want to break apart? Carbs. Yep. Carbs in the mouth primarily, and then when it gets to the stomach, it's proteins. So how do you control these? So control of gas excretion has 3 phases. Cephalic refers to what part of your body? The head. Yep. So here's the brain. When you start releasing these chemicals, it starts with the cephalic phase. You start thinking, I'm going to eat this sandwich. You look at the sandwich, you start thinking about it, you start releasing stomach acids and pepsin, your stomach starts moving more. How do you know that? Because if you don't eat right away, what's your stomach do? Right? It starts growling at you. It's getting active. It's releasing these chemicals, and it's getting ready to grind. It's just waiting for you to put something in it. You You don't even have to have the food in your body yet. The second phase is once the food gets in the stomach, then the stomach will start increasing these secretions. The stomach detects there's stuff in there and wants to break it apart, so it'll release mucus, pepsin, hydrochloric acid. It's trying to break the stuff apart. And then the third controller is the intestines. Once this food gets into the intestine, then the intestine can say, well, this is watery enough, this is dilute enough, it's basic enough, we're good, or it can say what to the stomach. Slow down movement and start releasing more enzymes. Why would the small intestine want you to release more enzymes now? It told the stomach slow down the movement, but release more enzymes. Why? Because that protein you just ate wasn't digested enough. So your brain's going to release lots of chemicals. It's going to turn up the motility or activity of the stomach. Your stomach, once it detects the food, is going to increase its motility and increase secretions. But the intestine, once you push the food in, if it's too thick or too dense, it slows the stomach down. And it'll also tell it release more enzymes, break down the protein. So if you ate a whole steak without like barely chewing it, that steak will sit in your stomach for hours and hours and hours, slowly breaking the proteins down. Okay, and the mucosal barrier. So the whole purpose of the barrier is to neutralize acids and prevent your stomach from eating you. If that barrier isn't working, then what's going to happen to the protein wall of your stomach? It's going to start eroding, is the term for it. It starts eating at the stomach, and what's that layperson term? It creates an ulcer. So the gastric mucosal barrier is preventing stomach acids from destroying the stomach wall. If they do get through, it causes an ulcer. H. pylori, what it does is it gets on the stomach wall and it destroys those cells so they can't release the mucus, and then the acid just follows behind it. It makes the ulcer worse. Okay, digestion in the stomach. Carb digestion continues just at the top, but briefly. The primary focus of the stomach is to digest what? Protein. This is where protein starts getting digested, and this is the primary focus of the stomach. Store food and digest the protein. And if you didn't catch this earlier, enzymes are made out of what? Proteins. When you release enzymes in your mouth and your saliva, when they get into the stomach, they're in a totally different environment. Those enzymes, when they get in the stomach, what do you think is going to happen to them? They're made out of protein, so what will probably happen to them? They'll get denatured and then digested. So carb digestion is just brief, right at the top of the stomach, until those enzymes get digested. What was the A word for the enzyme that comes from the mouth? Amylase. I feel like I'm asking this a lot, but what's the A word? What's the F word? And it makes me a little nervous sometimes what somebody's going to shout out. I like to think we're all grown-ups, but I'm not all the time, so I guess you don't have to be either. Absorption in the stomach, no nutrients, no food. So no proteins, no carbs, no lipids, no nucleic acids. None of these are absorbed in the stomach. Are any of them digested in the stomach? Yes, primarily protein, but absorption and digestion are not the same thing, and I'm going to try and push that really hard too. Digestion is the chemical breakdown. Absorption is the process of doing what with it? Bringing it into the blood. So no food goes into the blood from the stomach. It has to move down to the small intestine before the food can be absorbed. But alcohol and drugs like aspirin can. If it's an acidic drug, it has a tendency to get absorbed into the wall of the stomach, like aspirin. And then alcohol gets through. It's slower than if it gets in the small intestine, but it still gets through. It's just slower because it has to go through that mucus barrier. It has to go through the wall of the stomach, through all that thick muscle, and get into your bloodstream. Okay, so which is false about the stomach? How about number one? Oh, look, it goes through motility, secretion, digestion, and absorption again. How about motility of the stomach is peristaltic waves? That's true. Yep, that's the propulsive movement of the stomach. Number 2, a secretion of the stomach is pepsinogen. Is it secreted? Yep. Number 3, fat digestion begins in the stomach. What starts in the stomach? Protein digestion. So it looks like number 3 is our false answer. And number 4, no nutrients are absorbed. That's true. Can anything be absorbed in the stomach? Yep, alcohol and some drugs. Next organ. So if you look back, you can see all 4 processes: secretion, motility, digestion, and absorption in the stomach. Now the pancreas. Is the pancreas a primary or secondary organ? Secondary organ. So the secondary organ is there to help digestion, but the food never goes into it. There are 2 parts of the pancreas. There's exocrine and endocrine. Exocrine's pushing things into the GI tract. Endocrine's pushing things into the bloodstream. Yep. And then the little cells, we'll talk about these when we get to the endocrine system. The cells that are endocrine cells are called the islets of Langerhans. And they're like alpha, beta, delta cells. What's one hormone that's made in the pancreas that's released in this endocrine area? Wow, nobody knows this one? Insulin, yeah. So we'll actually talk about somatostatin again. Somatostatin's also made in the pancreas. We'll talk about something called glucagon. We'll talk about insulin. But yeah, insulin is usually the one people think about. And that comes later. So let's talk about the exocrine function first. So first you have enzymes that are released, and the cells are called the acinar cells. So the enzymes are released from the acinar cells, and we're going to talk about the enzymes in a lot of detail. The second type of cell is called the duct cell, and it releases this really watery substance. I always remember ducks love water. You think ducks would prefer acid water or basic water? Basic. So there again, have this really alkaline substance full of sodium bicarbonate. You actually have, I would guess, you have sodium bicarbonate in your kitchen. What's it called in your kitchen? Baking soda, right? But your pancreas makes this stuff, adds it to the water, and then squirts it in your GI tract. It specifically squirts it right into the small intestine, right into the duodenum, right after the stomach. Why would you secrete all of this sodium bicarbonate into the duodenum right after the stomach? To neutralize the stomach acid. Yeah, as the stomach acid comes in, it's neutralizing it. So acinar cells and then the duct cells. Like quack, quack, duct. Oh, wrong duct, sorry. And then you make about 2 liters of that solution a day. So just imagine taking an empty 2-liter bottle of soda, putting a bunch of baking soda in it, and mixing water. That's what you're releasing constantly all day. And it neutralizes the chyme. What was the chyme before it was chyme? A bolus, yep. So now it's full of stomach acid and enzymes, and it's called chyme instead. And there's the pancreas. You can see it sits right underneath the stomach. It's about 5 inches long, roughly. Pictures always make it seem gigantic, but it's not all that big. And it's constantly releasing things into this duct that comes down to the duodenum to neutralize stomach acid. It's also there to help break down proteins, carbs, and fats, which we'll talk about. Those are the enzymes. And then you have all these little islets of Langerhans that push things right into the blood. What are the things? What's the H word for the stuff that an endocrine cell pushes into the blood? H word. Hormones. Like insulin. Insulin doesn't get pushed into your GI tract, it's pushed in your blood to help you regulate sugars that get past the GI tract. Right, so the acinar cells, told you we'd come back and talk about it. There are 3 types of enzymes released. There's proteolytic, which means lytic is to break something apart. What do you think proteo is referring to? Proteins, yep. So proteolytic enzymes break apart proteins. They digest proteins even more. So once the food gets down to the small intestine, the pancreas releases an enzyme to help you break down proteins. More proteins. Because again, with enzymes are proteins that only work in specific pHs. So if pepsin works at a pH of 2, will it work at an extreme opposite pH of 8? Nope, it doesn't work anymore. So once pepsin gets into the small intestine, it's deactivated. It can't work. Same thing with salivary amylase. It works at a pH around neutral, around 7. Once it gets into a pH of 2, it's done. It gets neutralized and then it gets digested. Next are the pancreatic amylase. What does amylase break apart? Carbs, just like salivary amylase. Same stuff, different organ releasing it. And then pancreatic lipase or lipase, what's it breaking apart? Lipids. Right? So it's pronounced lipase, but if you think lipase, it's telling you it's an enzyme that breaks lipids. And this is the first time we've seen something break apart fats. You don't digest fats in the mouth, you don't digest it in the stomach. For the first time, you're going to digest it in the small intestine because of something that's made in what organ? The pancreas. Alright, so here are the 3 proteolytic enzymes. We're just fine-tuning and going deeper and deeper. You have to know all 3 of these, and they actually have a trick. If one of them doesn't work, the other 2 don't work. You have to activate one to activate the other 2. The first one that you have to activate is called trypsinogen. What do you know about it? It's inactive. Yep, it's an ogen, so it's inactive. Look at the second one, chymotrypsinogen. What do you know about it without me even telling you? It's inactive. Yep. So trypsinogen is inactive when it's released. It's released in the pancreas. I'll show you a picture. So it's released way up in here. Then it has to be moved all the way down this duct into the common duct and then into the small intestine where it's activated finally here. What would happen if you activated trypsin that is a proteolytic enzyme if you activate it inside the pancreas? What do you think? What do you think it would do to the pancreas? It would eat the pancreas. The pancreas is made out of proteins. So it would eat your pancreas. It would start digesting it. You have to move this all the way down to the small intestine to activate it. So trypsinogen works at a pH of about 8. What was the thing that worked at a pH of about 2 that digests proteins? What's the name of the enzyme that worked at the pH of 2? Pepsinogen. This is the equivalent of pepsinogen, it just works at a different pH. Pepsinogen worked at a pH of 2 in the stomach, trypsinogen will work at a pH of 8 in the small intestine. They're acid-base sensitive. Right. So now the thing that turns on trypsinogen, what activates it or pulls its pin, is not hydrochloric acid. Now it's a substance that's in the small intestine called enterokinase. It's an enzyme that activates an enzyme. Enzymes are interesting. They're usually like dominoes, where you don't just have one that magically works and does everything. It's usually one enzyme that turns on that other enzyme. We just usually don't mention all of the pathway. But this one's significant. So enterokinase is in the small intestine. It can never leave the small intestine. When we start talking about the small intestine in detail, I'll show you. It's actually stuck to the wall of the small intestine just to make sure it never leaves. Because remember, if that thing left the small intestine and went up this duct, what would happen? Well, if enterokinase starts activating trypsin up here, what would happen to you? You would start eating your own pancreas. That would be a bad day. Okay, so the active form of trypsinogen is called trypsin. And if you did have something that was letting it activate in your small intestine, you could actually inactivate it with something called a trypsin inhibitor. So people that get pancreatitis, what's it telling you is happening to their pancreas? It's getting inflamed and swollen. If something's activating trypsin inside the pancreas, it causes pancreatitis that swells. You can actually take a trypsin inhibitor that shuts that down. Number 2, chymotrypsinogen. Big word. The ending tells you it's inactive. Trypsin activates chymotrypsinogen. So you have to activate this one before that one will work. So here's where that pathway again. Enterokinase activates trypsinogen. Trypsinogen is now trypsin. Activates chymotrypsinogen to turn it into chymotrypsin. This breaks down more protein. And the third one, procarboxypeptidase. Pro means it's also inactive. It means before the active form. Procarboxypeptidase is also activated by trypsin. So if you blocked trypsin, if you turned it off, would any of these 3 work? No. They all depend on trypsin being activated. And then down here at the bottom, these are the 3 active forms. Trypsinogen becomes trypsin, chymotrypsinogen becomes chymotrypsin, and procarboxypeptidase becomes carboxypeptidase. This one's tricky because if you look at the beginning of this, you might want to think that it breaks apart carbohydrates. It doesn't. It breaks apart proteins into peptides. Those are the 3 proteolytic enzymes. So, which can you say is true about proteolytic enzymes of the pancreas? How about, hasn't gone 30 seconds. How about number 1? Does the pancreas release the active enzyme trypsin? No, it releases the inactive version of it called trypsinogen. Number 1's false. How about number 2? Trypsinogen is converted into trypsin by enterokinase in the small intestine. Yes. What was so special about enterokinase? It's what prevents it from going into the pancreas. It's stuck to the wall of the small intestine. It stays there. It doesn't leave. It can't leave. It's a safety feature. And we'll talk about it again when we get to the small intestine. So it looks like number 2 is our true one. Number 3, chymotrypsinogen is converted to chymotrypsin by mucus in the pancreas. What converts chymotrypsinogen? Trypsin, right. And number 4, procarboxypeptidase is released from the small intestine but is activated in the pancreas. What can you do to correct that? It's released from the pancreas and activated in the small intestine. Wrong direction. Okay, so pancreatic excretion is hormonally regulated to maintain neutrality of the duodenal contents. So hormones regulate it. Now we're going to have to talk about hormones. So here are the 2 major hormones that regulate the pancreas. The first one's called secretin. Both of these will go to the pancreas and release something, and I'll show you the hint here. They work on negative feedback loops. If you just had to go with your gut, always assume it's going to be a negative feedback loop unless I clearly say something else. So if secretin's final goal is to release something called sodium, what is this? HCO3 negative. Bicarbonate. If its final purpose is to release sodium bicarbonate, what did sodium bicarbonate do? Neutralized acids. So if its final effect is to release this chemical that neutralizes acids, what do you think turns on secretin? The presence of acid, right? So in the small intestine, if you release too much acid from your stomach into the small intestine releases this hormone called secretin that goes through the blood, comes all the way back around, and then goes to the pancreas. Once it's at the pancreas, it tells the pancreas, you need to start releasing this stuff to stop the acid. It's going to destroy the small intestine. The pancreas starts secreting this bicarbonate from what cells? The watery basic stuff came from what cells? Duct cells, right. And then it goes down down the pancreatic duct, down to the common biliary duct, and then finally out into the small intestine. Once it's in the small intestine, it neutralizes the acids. Once the acid is neutralized, what's going to happen to secretin? Secretin came out because you had too much stomach acid, so what's going to happen to secretin now? Now it's turned off, and this whole loop shuts down until you get more stomach acid in the small intestine. The second one's cholecystokinin. If you look for the negative feedback loop, its main purpose is to release enzymes to break apart lipids, fats, and carbs. Why would you release cholecystokinin in the first place then? If its main goal is to break down lipids, carbs, and fats at the end of its loop, it was turned on because you had too many lipids, carbs, and fats. Watch the loops. If you know what the purpose of this hormone is, the final effect of it, you know what releases it. Cholecystokinin, by the way, in your book is abbreviated CCK. And I think I abbreviate it in slides from here on out too. I just forgot to write it down. So cholecystokinin is CCK. So its primary stimuli that releases it is fat and protein. It's a hormone that travels to the pancreas, to the acinar cells, and it releases what breaks down fats. What's the other word for fat, by the way? A lipid. So lipase, right? And then proteins would be what? It wouldn't be amylase, that breaks apart carbs. It would be proteolytic enzymes. So they're telling you what they're breaking down. And I just walked you through the loop, but here they are. So when we get into the endocrine system, you'll be drawing a lot of these loops. Acid comes into the duodenum. The duodenum releases secretin. Secretin goes through the blood to the pancreas. Goes to what kind of cells in the pancreas? Quack, quack. Duct cells. And then the duct cells release that watery basic substance that goes all the way down into the duodenum and neutralizes the acid. Now the acid's gone, what happens to this whole loop? shuts off until more acid comes along to turn it back on. And then the same thing with CCK, because you have food in the duodenum, big chunks of food, lipids and proteins. CCK is released, it goes to the pancreas, to the acinar cells, and starts telling it, release your enzymes. It releases lipase, proteolytic enzymes, amylase, all of those to digest the food. Now the food's digested, do you need to release more CCK? No. CCK released the food, was released because of the presence of food. You've destroyed the food, so now it's gone. You stop releasing CCK. It's a feedback loop. Right? The aqueous sodium bicarbonate solution is the most abundant stuff, about 2 liters, a lot of that stuff. You release little bits of enzymes, but you release lots and lots of this sodium bicarbonate water. Where's it borrowed from? The plasma. Yep, it's borrowed from the plasma. That means it has to be recycled. What organ do you think recycles that water back into the plasma? So you're dumping it right now into the pancreas ducts. They go into the small intestine. Where do you think you recycle it? Primarily in the large intestine. Sucks a lot of the water back up and brings it back into your body. Next organ, the liver. Does the food actually transport through the liver? Nope. So what would it be? Primary or secondary? Secondary. And here, the primary purpose of the liver is not just to digest food. There are a lot of other things. We'll talk about these again throughout the semester. But when you look at the structure of the liver, it's made up of lobules, sinusoids, and hepatic cells. Here are the little lobules. You can see they're kind of hexagon shaped. They're kind of cool looking. And then the pathways for flow are sinusoids. They're little sinuses, little cavities for flow to go through. So you bring all of the blood from the GI tract up into the liver. It's almost like a disassembly line. You transport it down along this pathway to this main central vein. I'll show you. So it goes traveling, 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 traveling. And as it's going through, all these little hepatocytes are workers. Hepato means what? Liver. Cyte means cells. So it's just telling you the liver cells. As they're transporting down, it's pulling out nutrients. It's pulling out like copper, iron. It's almost like a little recycling system. Do you need copper? You actually do. Do you need a lot of it? No way. It can be bad for you. Same thing with iron. You can actually get too much iron. So as you're bringing these nutrients and these minerals down along here, you're extracting them. You're weeding them out, and then you just push what's left over in this major central vein, and that central vein will carry it up into the vena cava. So it's cleaning the blood for you. Anything that you just absorb, almost anything you absorb from the GI tract, goes along here, through the liver, gets cleaned, processed, and then that cleaned and processed blood goes up to the heart. This little thing, a Kupffer cell, it eats other cells. If bacteria gets in here, that Kupffer cell will eat it. What is a Kupffer cell then? You know this word. It starts with an M. It eats other cells. It's a big eater. It's a macrophage. Yep, it's just a special macrophage. The specialized macrophages that were in the alveoli were called alveolar macrophages. The specialized macrophages that are in the liver are called Kupffer cells. So if bacteria gets along in here, you can digest the bacteria and destroy it. Right. And then the other purposes, so what do these hepatocytes do? They help metabolize things. Metabolism doesn't mean just to burn. It can also be build. So they can clean up, they can process, they can stack together carbs, proteins, and fats. They detoxify things. So they have enzymes inside of them that will break apart alcohol, they'll process alcohol, process drugs, toxins, synthesize plasma proteins so they can actually make proteins. Albumin's an important one you'll want to remember later. We've actually already talked about it in blood, but albumin is the clear part of an egg, but it's the same stuff that's floating through your body. Your liver makes it to help you retain water and to carry nutrients through your body. Hormones, primarily, not just nutrients. And then storage of glycogen, fat, iron, copper. It's a storage site. Liver is actually pretty good for you as far as nutrients. Unfortunately, it's like the oil filter for your car, so too much of it can be a bad thing too. How many people have eaten liver? Gosh, like 3. It's amazing. My grandmother was from down south, so liver and onions was kind of a staple for her. About once every other week she would have it. It was delicious, I'll admit. It was awesome. Number 5, activation of vitamin D. Where's vitamin D made? Skin. It's activated at the liver, though. It's actually activated in 3 steps. It's made in the skin when you're exposed to sunlight. Then it's dumped in your blood, but it's worthless. Then it goes to the liver, and the liver modifies it a little bit. It's like an assembly line. It kind of tweaks it a little bit, and then it releases back into the blood, but it still doesn't work. It finally has to go to the kidney, and the kidney takes care of the final steps of activating vitamin D. Vitamin D is a complex chemical, but the liver is an important step. Number 6, removal of bacteria and worn out red blood cells. What's the other organ that helps you remove red blood cells? Spleen. And number 7, excrete cholesterol and bilirubin. So if you have too much cholesterol and you have a really good liver and you're genetically prone to it, you can actually push a lot of that bad cholesterol into your feces. You can modify it and get it all cleaned up so that you can get rid of it. People that don't handle cholesterol very well are usually the ones that you hear about having really bad cholesterol problems. Anybody know somebody that's eaten bacon and greasy eggs and they deep fry all their food and they've lived to like 95? It's just awesome because their liver rocks. Okay. And then bile is a chemical that's made in the liver. Bile, and I'm going to point this out really specifically, bile is made in the liver. Bile is stored in the gallbladder. There's a difference. Can you live without your gallbladder? Yes. Can you live without your liver? No. You can still eat all the same foods if you have your gallbladder taken out, but you have to modify the amounts of the foods because the gallbladder is storing a chemical called bile that helps you process. Anybody know? If you have your gallbladder removed, the doctor says you need to back off on what types of foods? Fatty foods. Bile helps you break apart fats. It doesn't actually digest fats. It breaks them apart. It's like hydrochloric acid didn't digest what? Protein. It just denatured or helped spread it apart a little bit. Bile does exactly the same thing. Bile just helps you process fat, but not actually digest it and break it apart. Right. So anyway, we've got a passway. So liver is making the bile. The bile is pushed all the way down here in the common bile duct. As it gets to the very end, if you haven't eaten food, this little sphincter at the end, sphincter vodi, will actually pinch off so that the bile won't go into the small intestine. Instead, the bile starts backing up. As it backs up, it goes up and into the gallbladder and starts accumulating there. The gallbladder will pull water out of it. It'll make it more concentrated. And if it sits there too long, it will actually compact it into a solid substance. Anybody know what that solid substance would be? A gallstone, yeah. But your body takes cholesterol, it turns it into these bile salts and uses it to break down and process fats. Gallbladder holds onto it, sphincter vodi. When you eat food, acetylcholine is released onto the sphincter vodi and it opens up. Acetylcholine is released onto the gallbladder and it starts squeezing it like a little horn on your bike. Honk, honk, honk. So the acetylcholine will squeeze that and push that bile out and down into the small intestine so that you can process fats. And then it starts moving along. At the very end of the small intestine, you'll start recycling some of those bile salts and bring them right back up to the liver so that you can reuse them. You don't make all that much bile salt, so you have to recycle most of it to be able to process fats. Right. And then I already talked about the Kupffer cells. Kupffer cells are just macrophages that are hanging out inside the liver. Okay, hepatic portal system. This is talking about a blood system. So it's the connection between the digestive tract and the liver. Every part of the digestive tract will actually push its blood into the liver. Well, I should say everything between the esophagus and your anus. If you absorb anything all the way down here, it will push it straight up to the liver unless it's a fat. Some of the fats don't go to the liver. The hepatic portal system carries all those nutrients to the liver. Why would it do that? So if it's from the esophagus, the stomach, the small intestine, the large intestine, all of that blood goes straight up and into the liver. What benefit would that be to you? What would you say the liver does? It cleans it, right? So if you absorb something, if something gets into the wall of your stomach, or if it gets into the wall of the esophagus, the lower part of the esophagus, or if it gets through the wall of the small intestine or large intestine, the first place it's going to go is the liver. If a bacteria gets pushed in here, it goes up to the liver right away. Macrophages in there are going to eat it, destroy it. When you bring in nutrients like carbs and proteins, those go straight to the liver to be processed. Fat is the exception to the rule. Some fat goes to the liver, but some fat actually gets around it. Because you have another way of transporting fluids in your body that's not the blood. What was the other system for carrying excessive fluids? Started with an L. The lymphatics. Fat, unfortunately, can slide right into your lymphatics and bypass the liver. That means fat can get up and into your vena cava without being cleaned, and then into the heart, and then into the pulmonary circulation, or even up and into like your coronary circulation. So fat can get right past this blood cleaning system. And that blood cleaning system is the hepatic portal system. It carries the blood up to the liver and cleans it. Hepatic portal system. All right, bile. So what's the purpose of bile? It doesn't digest, it emulsifies. If you use like soap, I'm trying to think of a good example. What's this stuff? My mom used to use stuff called Dawn, and I remember she made a lot of greasy food, and when she would put the Dawn on the top of the water, what happened to all the fat? It like breaks apart, right? In reality, microscopically, the fat didn't change its structure. It's exactly the same fat. All it did is it emulsified it. It turned it into little tiny droplets that weren't as easily seen. It's still the same fat. It just broke it into smaller droplets. That's what emulsification is. When you're eating this burger and there's fat dripping down your arm and you go, and you lick that off, and you get that into your intestines, that's a big wad of fat and a big puddle of water in there. What happens to fat when you put it in water? It just floats. They're all nasty like, right? So when it's all floating together, as soon as that gets processed and squirted into your small intestine, bile is secreted, and bile starts taking it and turning it from this big glob of fat into little microscopic droplets of fat so that it's easier for you to process. It's easier for your body to digest and break apart little tiny pieces than one big chunk. It's like the old story, if you're going to eat an elephant, how do you do it? One bite at a time. You don't try and eat the whole thing, right? So it's one bite. You process one little bit of fat, and then you can digest it. Process one little bit of fat, digest it. Little bites at a time. The little droplets are called micelles. There's a benefit to these. So you do want fat and you want cholesterol in your diet because these micelles that are made from the fats and the cholesterols will actually carry good things like fat-soluble vitamins. Anybody know the fat-soluble vitamins? A, D, E, and K. So these little fat droplets are actually good for you because they transport things like fat-soluble vitamins. And this is what they look like. I have to look up here because I can't see it on my screen. But here you have this little fatty droplet, this micelle. Here you have the bile salts sticking off the end. The bile salts are interesting because they're kind of like a phospholipid. So they're not charged here, they're charged here, so the non-charged head will stick into the fat, and then the water-loving end will sit out here. So it's surrounded by water, but it's this little isolated droplet. It's like taking a beach ball and making it into structures the size of marbles. And then you see it. There's the big beach ball up at the top, and you've broken into little marble-sized bitlets. And inside the middle of this, you can store cholesterol, you can store vitamin A, D, E, and K. Those fat-soluble things hide inside the fat droplet. They don't want to be out in the water. They're afraid of water. They're afraid of water. Phobic, yep. They're hydrophobic, so they're going to hide in here in the middle, and then you can transport them into your system. Carry them safely. They're protected. They go right through your small intestine, protected until they can get absorbed in. Okay. Next is the enterohepatic circulation. Right? This is a recyculating. That's my new word, recyculating. It's a recyculator. It's a recycling pathway so that, remember how I told you bile salts, you're limited to how much you can make. You can only make a couple grams a day, but if you eat a normal American diet, you need to make about 15 grams a day. So if you can't make that much, what do you do with the 3 grams you can use? Recycle it. Just keep using it over and over again. So what happens is as it's pushed out here, it works in the small intestine, but then it's recirculated back up to the liver, and it's reused. It's cleaned up, it's processed, and pushed back through. When it's old and worn out, then you can actually just poo it out, and it gives a yellowish-brown tint to your feces. So it's cholesterol. Cholesterol and bilirubin. What color does bilirubin turn you? Yellow. Yep, so your liver will take cholesterol and worn out red blood cells, the bilirubin from the blood cells, mix it together, make the bile salt, and when it gets too old and worn out, it just gets pushed and left out in the duodenum, goes to the large intestine, and then adds that brownish color to your feces, yellowy brown. Right. So I already said that. Bilirubin's made with pieces of red blood cell and cholesterol. And there the picture put together. So we have the pancreas down here, we have the liver up here. You can see you have the biliary duct, you have the pancreatic duct, and then they call this the common biliary duct as it's coming together, bloop, and it pushes into the duodenum. Both of these organs push into the same duct that goes into the duodenum. What's the name of the B word that the liver is making to help you digest food or process food? Bile. And then with the pancreas, there were three groups. There were proteolytic enzymes, there were the, what kind of amylase? I guess I could have put that the other way, pancreatic amylase, and then the third thing is the lipase. All these substances are working together. You eat food, your brain automatically tells your gallbladder start tweaking out the bile. It tells your pancreas start releasing the proteolytic, the amylase, and the lipase enzymes, and then you start filling this so you can break down the food right away. If you start putting food in here too quickly, do you remember the name of the enzyme that will come up here and start turning this up? It had three initials I told you to write down. Cholecystokinin, CCK. So you're looking at all the regulators, all the things that are turning these pathways on. Right. And here you go, stimulation for bile secretion. First is the presence of bile salts. If you start making too many bile salts, you'll start releasing them to get rid of them, especially those old worn out ones. So bile salts can stimulate the release of bile salts. If you have too much, you just start releasing extra. Secretin is another one. So when secretin is stimulated by acid, this is kind of the trick here. Secretin is stimulated by acid presence in the small intestine, but it will also release this bile to go down there and start working in the small intestine too. And the last one is the vagus nerve, which is primarily associated with what? What part of your nervous system? Parasympathetic nervous system. Parasympathetic sends a signal all the way down to the gallbladder and starts tweaking out the bile. Vagus nerve. What's the name of the neurotransmitter associated with that pathway? Acetylcholine. Oops. So what is the function of bile? What's it there for? So it's there to digest fat. What was the trick I told you about bile and hydrochloric acid? Neither of them digest anything. Hydrochloric acid denatures. What does bile do? Emulsifies, which I just answered this question. But so bile's there to work on fat, but it doesn't digest fat. It emulsifies the fat. What digests proteins? Pepsin or trypsin or chymotrypsinogen or procarboxypeptidase. Those all digest proteins. What does anything emulsify proteins? This isn't even a real term. What does hydrochloric acid do to proteins? It denatures them. And then I'm going to let you guess this. What actually digests fat? I mentioned it once. Actually, I mentioned it a few times, but I haven't talked much about it yet. What's the name of the chemical that actually does the digesting of fat? I'll give you a hint. It's an enzyme. Lipase, right? Lipase does. Right, the sections of the small intestine, we have a few minutes left. So the duodenum, the jejunum, and the ileum, they're in that order, starting stomach all the way down to the large intestine. The most activity is actually in the duodenum. The duodenum moves the fastest, it absorbs the most material, and it does most of the digesting. So as soon as you put food into the small intestine, most of its activity is right there at the beginning. The jejunum moves slower than the duodenum, it digests less than the duodenum, and the ileum moves the slowest and digests the slowest. It's almost like the duodenum's going crazy, squeezing up here, processing the food, but as it goes further, it kind of slows down, moves slower, because the food's already been processed mostly in the duodenum. Most of the nutrients have already been absorbed, so it's just you have this extra distance to get the last pieces out. Fast movement, slow movement. High absorption, low absorption. And I just said that. Duodenum's where most of the digestion and absorption occurs. And the last thing we'll talk about is this stuff called segmentation. So segmentation is a type of motility, but it's a mixing motility in the small intestine. Mixing. Guess what the propulsive motility is? Peristalsis. Yep. So the mixing motility is segmentation. And segmentation is kind of cool because what happens is here's a small intestine. Here's a lump of food, there's a lump of food. And it's almost like if you took a tube and you squeezed something in this side, what would happen to that stuff? It would smash to the other side, right? And then as you smash to the other side, you have to release this. And what happens to that stuff that's over here? It gets smashed backwards. So it's constantly going back and forth. I gave the example of putting all the ingredients for cookie dough into a bag, a Ziploc bag. It's the same thing. Put them all in there and then just squeeze one side of the bag to push it to the other side of the bag and then back. That's segmentation. It's taking one segment and smashing it to the next. There are two major benefits. One is it's mixing. The other one is it's giving all of the food a chance to touch the wall of the small intestine. Why would you want the food to touch the wall of the small intestine? To absorb it. The only way to absorb the food is for it to hit the wall. So if you have weak contractions and this food doesn't hit the wall, you don't absorb those nutrients. If you have something big and chunky in here and doesn't get a chance to make full contact with the wall, you can't absorb it. So segmentation is doing mixing, and it's also allowing you to absorb by making contact with the wall. Right, so mixing it with chyme, digestive juice, making contact with the absorptive surfaces, and at the very beginning, the basic electrical rhythm is going at about 12 beats per minute, you can say it that way, where the ileum is moving about 9. The beginning is moving faster to do more activity. The end is like, we don't have that much to do, so it slows down. And then when you get to the large intestine, it's going to go even slower, so you get a chance to absorb what primarily? All that extra water. And then migrating motility. Migrating motility is what P word? Peristalsis. And there it is right there. Peristaltic waves. And that's stimulated by a hormone called motilin. Motilin causes motility. So when the food's processed enough, the motilin comes out and says start propelling it. And then it inchworms its way through your small intestine. Until it gets to the very end, and this is the end of the motility, the ileocecal sphincter blocks off from going from, well, actually look at the name. Where's it at? Ileocecal sphincter, between the ileum and the cecum, right? Cecum's beginning of the large intestine, the ileum's the end of the small intestine. It's a sphincter. It's normally closed. This is a unique one though, because when it opens up, it actually opens like a valve. So as it opens, it allows your food to push this way into the large intestine, but why valve? Because valves prevent backflow. That way whatever's in the large intestine doesn't come back into your small intestine. It's a one-way flow. So as this thing releases, it opens up a little bit, pushes the food through. I have to be careful with my hand gestures here. It pushes the food through, and then it can't come back because the valve-like structure keeps it from closing. And here's your fun fact for the day that I'll leave you with. Gastrin we talked about up in the end of the stomach. You eat food and gastrin's released, and gastrin increases hydrochloric acid secretion, all that stuff we talked about before to process the food. But gastrin's a hormone, so how does it get around your body? The blood. Even to affect the stomach, it goes into the blood and comes back to the stomach. But as it goes down to this valve, the ileocecal valve, because you're putting food in your stomach, this valve opens up. Why? To push food through, right? It's saying, well, we've got food in our stomach, we need to make room in the small intestine, so let's open the ileocecal valve, we'll push the food through, and then we'll close it again. What's funny is that while you're eating the meal and gastrin's being released, I know you know this person, you may be this person. Do you know somebody that when they eat the meal, as soon as the last bite goes in, the plate is in the sink and they're in the bathroom, and they're not bulimic? It's because they go in there and then they're in there reading their newspaper or whatever they're doing in the bathroom for 15 minutes. It's because of gastrin. Gastrin's released. I thought this was hilarious because I used to have a roommate that before I was even done, he was like in the bathroom. And it's because gastrin releases and causes the food to move into the large intestine, which pushes more food into the rectum and stimulates that response, that defecation response. So it's just crazy how that works. I was about to make a joke that I'm surprised he didn't just eat in the bathroom, but I did find a lot of candy wrappers in there, so maybe he did. Isn't that the most disgusting thing? You walk in the bathroom, there's a food wrapper in the toilet, or next to the toilet. It's like, who does that? All right, That's it. We'll see you, well, upstairs for the case studies. Yep. Oh, unless I can get this. I'll check real quick and see if we can use the room, but I think on Tuesdays we can't. So let me stop this. Is there a quiz in lab today? No. Why? What are you supposed to be turning in today? Your digestive journals. That's worth the 10 points. So as long as you did that, it's an easy 10 points.